Hello there, Mr. Sutton here, bringing you the Algebra 2 9.5 lesson on making inferences from sample surveys. In this one, we are going to be estimating population parameters from samples. We will also be analyzing the accuracy of hypotheses using some simulations, and we're going to find margins of error. Before we get into the nitty-gritty of this lesson, a few general definitions to sort of set the stage here. What we've been dealing with for most of your high school career and in this chapter is actually a branch of statistics called descriptive statistics, which is where you're just organizing and summarizing data. So this includes all those lovely charts and data structures and mean, median, and mode and standard deviation. All that stuff is descriptive statistics. But there's another branch of statistics where you actually take the information that you've gotten about samples and use it to predict things about the population. We call that inferential statistics, where you're using a sample to make an inference or prediction about the real population. So the big revelation at this point in the game is that if you want to estimate a population's mean or proportion or whatever, you can actually do that by figuring out the sample's mean or proportion, and that will let you predict things about the population. So just in general, you can use a sample mean, and by the way, population mean, we use the Greek letter mu. With a sample mean, we use this little X bar to show that it's different than the population mean. So you can use a sample's mean and proportions to predict the population's parameters that are in the same category. With this concept in mind, here's a problem for you to try this out on. So we got some blue whale heart rates here, 36 of them to be precise. We want to estimate the population mean for heart rates for blue whales using what we've got here. And then also we want to estimate the population proportion of blue whales that have a heart rate that's greater than 10 beats per minute. So with this concept in mind, pause the video and see if you can come up with those estimates. All right, so again, if we're trying to estimate something about the population, we're going to try to get those values for the sample and hope that that's close enough at this point in the game. So for mu, we're actually going to use X bar. Again, that's our fancy way of saying our sample mean. And that's going to involve adding all these values together and dividing by 36. So I'm going to go to Desmos and start adding these. And I'm actually going to do all of that off camera because it's just a lot. So here I am on Desmos, and I've gone column by column and added all of these together. This right here is the first column you can see, and I added everything up to and including that final column with the 5 and the 9 at the end. That all came out to 331. And again, we're dividing that by the number of whales, which is 36 in this case. So let's go back to Desmos and do 331 divided by 36. And that gives us roughly 9.2 if we just take it to the nearest tenth. So that's the estimated average population heartbeats per minute for these whales. Now for the population proportion of whales that have more than 10 beats per minute, we're going to get the sample proportion for that statistic. So let's just count up how many of these are more than 10. So starting here on the left, we've got 1, 2, 3, 4, 10 doesn't count, 11 brings us to 5, 6, 7, 8, 9, 10, 11, and this is the last one, so that's a grand total of 12 of those that are greater than 10. So 12 over 36 then is our ratio, and this would actually, if we round it off, this is roughly 0.333. So that is our estimate of the population proportion. And just as a little point of reference, this fancy looking P, if you notice that it's not quite the same as these other P's here, this is actually the Greek letter rho, which is another way of talking about the population proportion. So I hope you enjoyed that last problem on figuring out blue whales' heart rates. But if that wasn't quite your jam, here's another situation where we might want to be able to make predictions about the population and how it feels based off sample sizes. Let's say that we have a website trying to predict the winner of a city's mayoral election. So maybe this is Zootopia, and we have a choice of predators to be in charge. And this could be a very important result for this election. So let's call these candidates A and B. And let's say we have 8 staff members conducting surveys of randomly selected residents who are asked whether they will vote for candidate A, just yes or no. And here's the results. So for each of these results, they've listed what their sample size was. That's how many people they asked, the number in that sample that said they're voting for candidate A, and they were nice enough to calculate all the percentages for us as well. So they want to know, based on the results, this is a two-part question, based on the results of the first 2 sample surveys, these 2 right here, do you think candidate A will win the election? Explain. And then, based on the results in the table, and by this we mean all the results in the table, all the different samples, do you think candidate A will win the election? So same question, just, we're considering the first 2 surveys, and then we're considering all the surveys. Now, one thing that can guide you as you answer this using kind of your intuition is that larger sample sizes, as you might expect, are going to give you more accurate predictions. So with this in mind, pause the video and see if you can call this election. All right, so let's do part A here. So just based on these first 2 surveys, in this one, candidate A is getting under 50% of the vote for both of these. And in the larger of the 2, candidate A got even less of the vote than the smaller sample size. So this seems to indicate, just based on these first 2, that candidate A will not win the election because we're under 50% for both of those surveys. But if we expand our query to the rest of these surveys, well, it's a different story. After the second survey, candidate A is getting well over 50% of the vote in all of these cases, especially in the larger ones here. So this would seem to indicate that candidate A should win because our largest sample size surveys are putting the candidate at over 50%. So yes, over 50% with the largest sample sizes. Now, if the only sample where the candidate won was this last one, I mean, that might argue for candidate A, but we might want to rethink it because all these other samples, even though they're smaller, still add up to more than 200 people. So we might need to take that into account if it was just this one survey. But come on, it's the other 6. So I think candidate A is probably a lock for this position. For this problem, we're going to try to analyze a hypothesis here using a simulation. So here's the backstory. A polling company claims 34% of U.S. adults, like Homer here, say that math is the most valuable school subject. I couldn't agree more. To test this claim, though, because you're not just taking it at face value, you survey a random sample of 50 adults, and then you run a simulation of 80 random samples of size 50 for 34%, giving the distribution below. And we'll talk a little bit more in a minute about what this actually means. Based off this, we want to know what we can conclude about the accuracy of this 34% claim when 15 adults in your survey say math is the most valuable subject, and do the same kind of reasoning if you had 25 adults saying math was the most valuable. All right, let's back up a step here. So if this 34% claim is true, what that means is that 34% of all the people in the United States are saying this about math. That means if you pick any random person, there should be a 34% chance that they say math is the most valuable. Now, when you randomly sampled 50 adults, does that mean that you're going to get exactly 34% of them saying that math is the most valuable subject? Well, you might. You also might not. It depends on which adults you pick. There's a lot of variation over the 300 some odd million people. I mean, if you go to a math conference and ask them what's the most valuable subject, you might get something closer to 100%, right? So there can be a lot of variation. So it can be helpful to sort of figure out what sort of variation we might expect if we're doing this sort of random choosing. To help us figure out what to expect, we have the computer basically do your survey. They said we ran simulation of 80 random samples. So we basically had the computer do your little survey 80 times and came up with these different results. Now, what did your computer actually do to run your survey 80 times? Clearly, it didn't go out and ask people, 50 adults 80 times what they thought. The computer doesn't interact at all with the human beings. What your computer did was it essentially had 50 random number generations for each of these surveys. Your computer picked a number between 1 and 100, and it just counted up how many of those numbers were between 1 and 34. You can think of it as like playing a game where you have a 34% chance of winning every time you roll the dice. And the computer just rolled the dice like 50 times and saw how many times you won that particular game. And then it did that 79 more times. So as a result of doing this 34% sort of game, here's what your computer came up with. It found that if you look at the 0.34 here, 8 times you actually did get 34% of the time that you won. But if you look here, you actually got 32% even more often. And there was one time where you got like 52%, even though you only had a 34% chance of winning. You got really lucky on this one. And, I mean, lucky if you like math, I guess. And then there was these 18% where you were not so lucky. So these are kind of all the expected values of what we might get. So with that in mind, all you have to do is just compare the values that you got with your proportions to what you see here, and that'll tell you whether or not this claim is likely, accurate, or not likely to be accurate. So with that in mind, pause the video and evaluate the claim for 15 adults and also for 25 adults out of 50 saying that they love math. All right, so let's find our proportion for 15 here. 15 over 50 is giving us a proportion of 0.3. Looking that up in our table, that's right here, we see that there's a relatively high frequency of times that our simulator came up with 0.3. So that means that the claim is likely to be accurate. This 34% might actually be true. Now, looking at our other sample that we ran with 25 adults, 25 over 50 is 0.5. Looking at 0.5 in our table here, that's right here, that has a pretty low frequency, and it's also surrounded by low frequencies as well. So given this very low frequency, the claim is likely inaccurate that 34% of the true population actually believes this way, if you're getting 50% when you randomly asked people. Now, if that's not totally convincing to you, you could do more samples, or you could conclude that maybe the true value is closer to 50% than 34%. I'll let you decide how you want to handle that. But that's what your survey is telling us. Now, this next part of the question, they said, assume that the true population proportion is 0.34. Estimate the variation among sample proportions using samples of size 50. What they're basically asking for here is if 0.34 is the true percent value, the true chance you have of getting someone that says math is valuable, then what's sort of the range of these random probability values that we would expect if we were to build a distribution based off of that? And we already have a distribution, so we can use that to answer this question. What they're basically asking for here, in terms of what's reasonable, they're asking for what values are in the middle 95% of this proportion distribution. Now, why 95%? It seems kind of like a random number. Well, you might remember when we were talking about normal distributions, which this one does have that nice sort of bell-shaped curve almost, that 95% of the data was within 2 standard distributions of the mean. So that's where this 95 is actually coming from. So with that in mind, where's our middle 95%? Well, to figure that out, it would be nice to know like how many dots are actually 95% of the simulations. They ran 80 of these simulations. What's 95% of 80? Well, let's go to Desmos. So 0.95 times 80 gives us 76. So 76, we want the 76 middle dots, which means that we need to chop off the 4 kind of outer dots, 2 on the left and 2 on the right. And that's actually what these red dots represent if you were kind of wondering why are some of these blue and some are red. These red ones are the ones that are outside of this 95%. So that means that the blue dots, where the 95% begins, we have one over here and a couple over here. And those values are going to be 0.2, that's this value right here, and this other value here is 0.48. So those are kind of the expected values that we should get if we're within that middle 95%. So as that last problem we did with that simulation kind of bears out, we're very unlikely to get the exact population value when we run a sample. For that reason, and people who do statistics kind of know this, for that reason, claims about a population often include what is called a margin of error. And here's an example of this just to give you some context. So let's say that a survey finds that 34% of Americans think math is the most important subject, and here's the crucial part, with a margin of error of plus or minus 2%. So I just kind of made these numbers up. But what does this margin of error piece mean? Because you might have seen this also when news organizations were publishing poll results about candidates. The margin of error, which we could call the MOE for short if we need to, is the maximum expected difference between a sample value and the true population value. So basically, it's a measure of how far off we think our answer could be from the true answer. And you might wonder, well, what's this whole expected piece? How far off are we expected to be? And expected by a common statistical convention means 95% of the time. Just over the years, statisticians have guaranteed that if we can be like 95% certain, that still leaves a little bit of wiggle room for statistical weirdness, but it's close enough that we can do functional things with the information. So just to kind of translate this example in light of our definition here, what this up here is really saying is that, hey, we are 95% confident, that's that 95% piece, that, well, this is plus or minus 2%, so 34 minus 2, 32%, to 34 plus 2, 36%, 32 to 36% of Americans actually think math is the most important subject. So we're saying, hey, we don't know exactly how many of them feel this way, but it's somewhere, we're pretty sure it's somewhere between 32 and 36. And that might not be as exact as everyone would want us to be, but it's close enough to let us do something with the information. So because of this functional purpose, it can be very important to be able to figure out a margin of error for any data that you're reporting. How do we go about doing that? Well, there's a couple different situations we're going to go through. Let's say that we know the standard deviation of our data set. How can we use that to find the margin of error? So just to kind of go back to the first lesson in this chapter, recall that 90% of values in a normal distribution, 95% of normal values, are within 2 standard deviations, which we could call 2 sigma, of the mean for that population. So since we want to be 95% confident in our results, and 95% means 2 standard deviations, that means to figure out what our margin of error is, for a relatively normal data set, we literally just have to do 2 times the standard deviation. And that will give us our margin of error. So with this in mind, let's give this a test run. Let's say that we have a distribution of data with a population proportion of 0.34. And let's say that this has a standard deviation of about 0.04. Based on this, find and interpret what the margin of error is for this. Pause the video, give this a shot. All right, so calculating the margin of error is pretty easy in this case because they gave us the standard deviation. We're just going to do 2 times 0.04, which is, I don't even need a calculator, this is just 0.08. So what does that actually mean? This means that 95% of the data is going to be within 0.08 of your population proportion of 0.34. Or to be more specific, 95% of your sample proportions that you get are going to be within that range. So we know how to calculate margin of error if we have the standard deviation. But what if we don't? Well, another piece of information you might have access to might be the sample size of your data set. So it turns out there's a handy formula that will allow us to approximate the margin of error if we know the sample size. If we have a sample size of n, then we can use the formula margin of error equals plus or minus 1 over the square root of n. And this will give us our margin of error expressed as a decimal. Now you might wonder, well, where is this formula coming from? And we're not going to go into all that. But if you're looking to look this up on YouTube or Khan Academy or something, it's tied in with the formula for standard deviation and also something called the standard error. But we're not going to delve too deep into that. We're just going to use it. So here's something you can use to give this a test drive. We want to find the margin of error for a survey that has a sample size of 260, and then just round your answer to the nearest tenth of a percent. Pause the video, give it a shot. All right, let's see how this went. So using my formula, pretty straightforward. I'm just going to do plus or minus 1 over the square root of the number they gave me. Nothing super crazy here. Let's go to Desmos to figure out what that is. So here I am on Desmos. Let me do 1 divided by, and then SQRT, square root of 260, and I instantly get the value 0.062. So if I move my decimal over by 2, that means I have a margin of error of plus or minus 6.2%. Now that we can calculate margins of error using sample size, let's use this in a real-life context. In a survey of 1,509 U.S. adults, 47% that they actively try to include organic foods in their diet. Good for them. And we want to give an interval that is likely to contain the exact percent of U.S. adults who actively tried to include organic foods in their diet. So we're recognizing that this 47% might not be the exact percent, but we want to use margin of error to figure out what range that exact percent falls in. So a couple steps here. First, finding the margin of error would be very helpful here, and we have a formula for doing that. And also, once you've got that, again, that's just telling you how far away from this value the exact percentage could be at most. So if you add and subtract your margin of error to the percent they give you, that will give you your range. So pause the video and give that a shot. All right, so first step, finding the margin of error. We're going to do plus or minus the 1 over the square root of 1509. That's our 1 over square root of n formula again. Let's run those numbers. So I've got 1 divided by square root 1509. And that comes out to, if we make this, just round this off to the nearest tenth of a percent, this is going to be 2.6-ish percent. So we're just going to add and subtract that to the 47. That's what this plus or minus really means. So we have 47 minus 2.6. That's going to be the lower bound of the exact percentage. And we also have 47 plus 2.6 as the upper bound. 47 minus 2.6, that's going to be, let me think, 44.4, which is kind of a nice number. And the upper bound on our percent is going to be 49.6%. So that's where that true percentage is going to fall in. So to wrap things up, one question some of you might be having is how big should we make our sample size, kind of in light of this margin of error situation? We've seen that the larger your sample size is, the smaller your margin of error is going to be. So how big should we go? Well, a lot of it's going to depend on how accurate you need your results to be. I mean, is knowing that the number of people who want to include organic food between these two values, is this a good enough approximation for you, or do you need more accuracy? Let's say that we wanted to get this margin of error down to 1%. Just to show you on Desmos what that would look like, that would mean instead of doing 1509, I'd need to do the square root of 10,000. 10,000 people would bring me down to 1%. So, you'd have to do another 8,500 people to get that level of accuracy. Is it worth it? Well, I'll leave that choice to you. Until next time, Mr. Sutton, signing off.